Hello there. In the last couple of videos, we discussed several properties involving the expected value and the variance of discrete random variables. In this video, we're going to distribute or develop two particular properties that are extremely important. Let us assume you have a series of n-size samples. So let's assume there's several of your friends, and they go out to this population and gather, say, 50 samples each. And let us assume these samples are independent. And let's assume that we're drawing from the same exact population, and the mean of that population is mu, and the variance of that population is sigma squared. So what kind of properties can we develop from this? So let us make a couple of observations here. Firstly, since these samples S are independent samples, each xk is a random variable in their own right. Because if you have some sample 1 which contains values x1 all the way out to xm, and s2 is another set of values, say x1 out to xn, and you have a bunch of these samples, then pretty much x1 out to xn, these values here are random variables that pretty much say, okay, you know, what is the probability that x1 is this, or that this one is that, and so on. So capital X1 pretty much represents the random variable of all the possible values that x1 can be, and same goes for all these other values. So for this particular sample here, if I take all these values and average them up, so we can define this x bar to be equal to 1 divided by n times the summation of these random variables. Here, k is going to range from x1 to n. Then this right here also is a random variable. And keep in mind that each of these values are independent from one another. And this value here is a random variable. So I can talk about the expected value and the variance of these objects, which is pretty much the highlight of this video. So let us talk about the first main property that we want. So what is the expected value of this sample mean? So keep in mind here, this is going to be the expected value of 1 divided by n times the summation from k is equal to 1 to m of each of these variables xk. And here I'm just pretty much replacing this value in place of x bar. So remember, n is fixed, so 1 divided by n is a constant. So I can factor that outside of the expected value, because recall, the expected value of a constant times a random variable is just equal to that constant times the expected value of that random variable. So this is going to become 1 divided by n times the expected value of the sum of all your random variables, where k is equal to 1 to m. Also recall another property, that the expected value of the sum of two random variables is equal to the sum of their expected values. So I can interchange the expected value and the sum in this expression, and that's going to give me 1 divided by n times the sum from k is equal to 1 to m of the expected value of xk. So it's the sum of all the expected values for each of these random variables. So I can rewrite this in expanded form. So this is the expected value of x1 plus the expected value of x2 all the way down to the expected value of xn. And remember, x1, x2 all the way down are all random variables from RVs from the population P. And remember, P has a mean mu and a variance sigma squared. So the expected value for each of these variables is going to be the mean of the population for which they're associated to. So that means this is going to come out to 1 divided by n times mu plus mu added up n times. So that means this is going to be equal to 1 divided by n times mu. And here you can see this n on the bottom and n on the top will cancel. So then I'm just left with mu. So that means the expected value of the sample mean is going to be equal to the mean of the population, which is extremely important. And some people will rewrite this instead as mu x bar is equal to mu. So let's take a moment and pretty much explain exactly what this says. So this is sometimes referred to as the mean of the sampling distribution of sample means. And this value, again, is the traditional mean of the population. So remember the idea of statistics, mu is usually never known, but you can always take samples from that population. So if you take a series of n-size samples and average all of them up, eventually the average of all those sample means is going to be really arbitrarily close to the mean of the population. So this pretty much gives us a tool for figuring out what mu most likely is, even though we cannot get it directly, simply by taking samples, independent samples from the population. So let us derive the second property. What is the variance of x bar? So again, we're going to start from the definition of what x bar represents. So that's going to be equal to 1 divided by n times the sum from k is equal to 1 to n of each of our random variables x. So recall that the variance of a constant times a random variable is equal to that constant squared times the variance of that random variable. So we can take this constant 1 over n out, but if we do, we have to square it. So that means this is going to be equal to 1 divided by n squared times the variance of the sum from k is equal to 1 to n of xk. So let us remember an important property that we stated in the beginning. Here, xk are independent random variables. That's the first thing. So if these xk's are independent, there's a property that we can use, namely the variance of x plus y is equal to the variance of x plus the variance of y. And that's only if these variables are independent. If they're not, we cannot use this property. So that means this is just going to be equal to 1 divided by n squared times the sum from k is equal to 1 to n of the variance of xk. So I'm going to expand this out so we can pretty much see what's going on here. So this is going to be equal to the variance of random variable x1 plus the variance of random variable x2 all the way down to the variance of random variable xn. So remember, x1, x2, xn are all coming from the same exact population p. So that means they all have the same exact variance, namely sigma squared. So that means this is going to be equal to 1 over n squared times n times the variance of the population. And here, one of these n's will cancel. So that means we're just left with sigma squared divided by n. And that is the variance of the sample mean. Or we can rewrite this as sigma x bar squared is equal to sigma squared divided by n. So let's explain this and see exactly what this is talking about. So this expression here is the variance of the sampling distribution of sample means, which means what? So if we take all of those sample means and put them in a set, this describes how these sample means are varying with respect to one another. So if the variance of the sampling distribution is extremely large, that means all of these samples that we have, their sample means are really different. But if this variance of the sampling distribution is really small, then that means all these sample means are going to be really close together. And again, sigma squared is the population variance. And n here is the size of the samples. So that means we can also get the property, the standard deviation of the sample mean, just by taking the square root of the preceding equations. So that's going to be sigma divided by the square root of m. Or we can write it in the more traditional sense, namely sigma x bar is equal to sigma divided by the square root of m. So here, this is the standard deviation of the sampling distribution of sample means. So standard deviation of the sampling distribution of sample means. And sometimes people will refer to this as the standard error of the estimates, x bar. So these are the two main properties that are associated with sampling distributions, the sample mean, and the expected value and variance of it. So let's pretty much summarize this in a very neat way. So summary. So let us assume we have a population P, which has mean, mu, and variance, sigma squared. And we take a bunch of samples from this population, as many times as we want, preferably a lot of them. So a lot. And how many is enough? Well, that sort of depends on other things. Such that each of these samples has sample size n. And usually we want the sample size to be as large as possible. So if we take all those values and pretty much map them on some graph, and we're going to get some distribution, right? Then the expected value of that sampling distribution is going to be equal to the mean of the population. So usually we write this as mu x bar is equal to mu. And the variance is going to be equal to sigma squared divided by m, which we sometimes write as sigma squared x bar. And most importantly, the standard deviation of x bar is going to be equal to sigma divided by the square root of n, which we usually just write as sigma squared x bar. And this is what we refer to as the standard error of the estimate. And these two properties we will see again very shortly, but at least take note of these values and understand what they mean. So pretty much if we take a bunch of samples and take their averages, that's going to be mu x bar, and this thing is going to be approximately equal to mu. And we've proven that the expected value of those sequences is going to be exactly mu. And also, if we continue this process and we calculate the standard deviation of those sample means, it's going to be equal to the standard deviation of the population divided by the square root of the sample size. And note here another quick property, that as n gets arbitrarily large, the standard deviation of the sampling distribution of sample means is going to get arbitrarily close to 0. So if we have large samples from the population P, then that is going to make this sigma x bar get close to 0, which means the error in approximating x bar, so that means x bar usually is a statistic for the population, this is going to be really good of an estimate for the population mean. And that's a quick summary of these two properties and how to interpret them.